Through the past two playlists, I have introduced various notions related to integrals that are related to each other but distinct. They use similar notation, but they mean different things. We have definitions, geometric interpretation, notation, and various theorems that allow us to compute things quickly in practice. I have introduced these concepts one by one, but sometimes we may confuse them with each other. So, in this video, I will present a summary of all these concepts, I will compare them side by side, and I will summarize the definitions and the results. We have learned three concepts. First, the definite integral. Second, the indefinite integral. And third, how to define a function by an integral. And these are different. The definite integral, the integral from a to b of a function f, is a number. But the indefinite integral, when we say yes, the integral of f, that is a collection of functions, a set of functions. And finally, when we define a function by an integral, like big f of x is the integral from a to x of little f of t dt, then that is a single function. So a number, a set of functions, and one function. They're different. Let's go through them one by one. First, the definite integral, the integral from a to b of f of x dx. We had a formal definition and a geometric interpretation. The formal definition is the only rigorous one, but the geometric interpretation is much easier and cleaner to understand. I remind you the formal definition, which was complicated. We first need to compute the upper integral as the infimum of all the upper sums, and the lower integral as the supremum of all the lower sums. And if those two quantities are the same, then that's what we call the integral. As a formal definition, that's quite complex. The geometric interpretation is simpler. The definite integral represents simply area under the curve, as shown by this picture. If the function is positive, otherwise I need to take care of the signs, then the definite integral is the green area, the area under the graph of f above the x-axis from x equals a to x equals b. So we have a formal definition and a geometric interpretation. But in practice, how do we compute a definite integral? We want to avoid having to use the formal definition for computations at all costs. This is where we have a theorem, the fundamental theorem of calculus, part 2, that comes to save the day. This theorem says that if I want to compute a definite integral, first find one antiderivative g of f by any means necessary, normally by guessing. And then the integral from a to b of f is simply going to be g of b minus g of a. That's it. For example, I want to calculate the integral from 1 to 2 of x squared dx. First, I need to find one antiderivative of x squared, and 1/3 of x cubed works. And then I need to evaluate it at 1 and at 2. So that comes out to be 8/3 minus 1/3, which is 7/3. It is a number, as it should be, and this is certainly much easier than using the formal definition. Moving on to the second concept, the indefinite integral, the integral of f of x dx. The definition is, this is the collection of all antiderivatives of f, and that is why the indefinite integral is a set of functions. But again, how do we compute it in practice? Here, we also have a theorem that tells us what to do. In this case, the theorem is a consequence of the mean value theorem. And it says, first, find one antiderivative g of f by any means necessary, and then we can simply write that the integral of f of x dx is g of x plus an arbitrary constant c. As long as we are in an interval, we only take integrals over an interval. For example, if I want to calculate the integral of x squared dx, first I find an antiderivative, 1/3 of x cubed works, and then plus an arbitrary constant c. The third concept is a function defined by an integral. For example, big f of x is the integral from a to x of little f of t dt. In a certain way, this is a definite integral because it's the integral from a to x, except that the second end of integration, x, now I'm not thinking of it as a fixed constant, but as the variable of a new function big f. So for each value of x, I get a different number, and that's why this is a function of x. As long as the function little f is integrable, then this is a perfectly valid way to define a new function. This is just a new function. But what do we know about it? Here we also have a theorem, is the fundamental theorem of calculus, part 1, that tells us that if, in addition, we assume that little f is continuous, then this new function, big F, is an antiderivative of little f. So this gives us a way to construct an antiderivative. For example, I define a function big F of x as the integral from 3 to x of e to the minus t squared dt. This is a valid way to define a function, and this function satisfies that its derivative is e to the minus x squared, and also it satisfies that f of 3 is 0. And in fact, it's the only function satisfying these two properties. They completely determine it. And we don't write this function in any simpler way because there is actually no simpler way to write it. It often happens that this is the only way to construct an antiderivative, but that's okay because it's a valid way to define a function. To conclude this video, why do we sometimes write the x and sometimes the t? Can we change between x and t arbitrarily? Well, it depends on which one of the three things we are doing. If we are computing a definite integral, the result is a number, and there is no intrinsic meaning carried by the variable x. You can call it x or you can call it anything else. So if I change the x's into t's, the answer is the same, or into any other letter. It doesn't matter. However, if I'm calculating an indefinite integral, then there is sign meaning to the variable x, because the outcome is a collection of functions whose variable is x. So if I change all the x's into t's, the result is not equal, because now I will get a collection of functions whose variable is t. So it matters which variable we are using in this case. Finally, if I'm defining a function via an integral, then what happens? For example, if I consider the function f of x as the integral from 3 to x of e to the minus t squared dt. Well, in this case, I can use any letter I want as the variable of integration. Instead of t, I could perhaps write u, or perhaps write something else. However, the one thing I am not allowed to do is call it x, because x already means something else in this problem. So never write something like the integral from 3 to x of e to the minus x squared dx. Because in this case, x has two different meanings in the same equation. It's the variable of the function f and the variable of integration, and that is not allowed. That is meaningless, that could be ambiguous, so never write something like that.